Hi friends, in this video we'll discuss about the joint random variables if both random variables are continuous. So if x and y are two random variables of continuous and they are of two-dimensional. So if x comma y is a two-dimensional discrete random variable, then the joint function of capital X comma y is known as the joint probability mass function, and it is denoted by p of x comma y and defined by p of x comma y of xi comma yi equals to p of x equal to xi and y equal to yi if x equals to xi and y equals to yi and 0 otherwise. Now we'll see if it is that is for the discrete random variables x and y. If what happened if x and y are both are continuous random variables, then the probability density function that x of x comma y is a random variable of two-dimensional space, then the joint probability density function of f of x comma y of x comma y and defined by f of xy of x comma y equals to probability of x equal to x and y equals to y. Also, the probability density function is obtained by differentiating the probability distribution function, or which we can say probability cumulative function too. So that is, if capital F of x comma y is a probability distribution function, then small density function f of x comma y equals to derivative of capital F of x comma y, or capital F of x comma y equal to double integration 0 and minus infinity to plus infinity minus infinity to plus infinity of small f of x comma y dx dy. So if two-dimensional random variables x comma y, a function f of capital X comma capital Y of x comma y, capital X capital Y of x comma y is said to be probability density function if and only if integration minus infinity to plus infinity, integration minus infinity to infinity, f of x comma y dy dx is equals to 1. Now we'll see what is the marginal probability distribution function of x. The marginal probability distribution of capital X is denoted by capital F of x and defined by capital F of x equals to integration minus infinity to plus infinity f of x comma y dy. Similarly, the marginal distribution function of capital Y is denoted by capital F of small y and defined by capital F of small y equals to integration minus infinity to plus infinity f of x comma y dx. Now, conditional probability density functions. The conditional density functions of capital X equal to x for given y of y is denoted by f of capital X by y of x by y and defined as f of x by y of capital X by y of x by y equal to capital f of capital X y of x comma y by marginal density, marginal function of y. So similarly, f of y capital Y by of x, that means the conditional density function of y equal to y for given x equal to x is f of capital Y by x of y by x is equals to fxy of x comma y by marginal function of x. Now I'm going with an example. The joint probability density function of two-dimensional random variable capital X comma y is given by f of x comma y equal to 2 for 0 less than or equal to x less than or equal to 1 and 0 less than y less than x and 0 otherwise. Then find the marginal density functions of x and y. Find the conditional density function of x for y equal to y and conditional density function of y for given x equals to x. Now we have minus infinity to plus infinity, minus infinity to plus infinity, f of x comma y dx dy, where f of x comma y is the probability density function. Then integration 0 to 1, 0 to x, f of x comma y equal to 2 into dy dx. So 2 times of integration 0 to infinity y from 0 to x dx. So 2 into integration 0 to 1 x into dx. So 2 times of x squared by 2, then I got the 1. So I got integration minus infinity to plus infinity, integration minus infinity to plus infinity, f of x comma y dx dy equal to I got 1. So definitely f of x comma y is a joint probability density function. So I have to find what is the marginal density function of fx of x. So minus infinity plus infinity f of x comma y dy. So integration 0 to x 2 into dy. So 2x is the marginal probability density function of x. Similarly, marginal probability density function of y is equal to integration minus infinity plus infinity f of x comma y dx. So integration 0 to 1, 2 times of dx is nothing but 2. Now, what is the conditional density function of x for given y equal to y? So we denoted by f of capital X by y of x by y defined by xy of x comma y by fy of y. So 2 by 2 by 2 is equals to 1. Similarly, what is the conditional density function of y for given x equal to x is f capital y by x of y by x is equal to fxy of x comma y by marginal density function of x. So 2 by 2x. So is nothing but 1 by x is the answer. So we'll go with one more problem. Suppose a random variable capital X comma y have the joint density function defined by f of x comma y equals to c times of 2x plus y, where 2 is less than x is less than 6 and 0 is less than y less than 5 and 0 otherwise, then find the value of c and probability of x greater than 3 comma y greater than 2, probability of x greater than 3 and probability of x plus y less than 4. So we know that a function is said to be probability density function if minus integration minus infinity to plus infinity, integration minus infinity to plus infinity f of x comma y dx dy equals to 1. Now I will show that this function is a density function. So integration 2 to 6, integration y equal to 0 to 5 of c times of 2x plus y into dy dx. So c times of integration x equal to 2 to 6. So if I'll integrate with respect to y, then 2xy plus y square by 2 from the limits 0 to 5 dx. Well, substitute the limit c times of integration x equal to 6, 2 to 6, 10x plus 25 by 2 dx equals to 1. So is equals to, again, if I integrating with respect to x, so c into 5x square plus 25x by 2 from 2 to 6 is equals to 1. Then I'll get c equals to 1 by 210. Then my probability density function f of x comma y equals to 1 by 210 into 2x plus y, where 2 is less than x is less than 6 and 0 is less than y less than 5 and 0 otherwise. Now I have to find what is the probability of x greater than 3, y greater than 2. So lower limit is for x is 3, lower limit for y is 2. So integration x equal to 3 to 6, integration y equal to 2 to 5 of 1 by 210 into 2x plus y dy dx is equals to 1 by 210 into 2xy y square by 2 from 2 to 5. So is equals to 1 by 210 into integration x equal to 6 to 3, upper limit 10x plus 25 by 2 minus lower limit is 4x plus 2. So the answer is 1 by 210 into integration x equal to 3 to 6, 6x plus 21 by 2 dx. So 1 by 210 into, again if I'll do the integration 6x square by 2 plus this 121 by 20x. If I substitute the limits, the answer is become 1 by 210 into 81 plus 63 by 2, which is 15 by 28. Now what is the probability of x greater than 3? That means y is from 0 to 5, x is from 3 to 6. So 1 by 210 into 2x plus 5 dx dy. So 1 by 210 into, if I'm doing integration with respect to x, then 2x, 2 into x square by 2, 2 to getting cancelled plus xy from 3 to 6. So 1 by 210 into y equal to 0 to 5, 36 plus 6y minus 9 minus 9. 36 minus 9 by 27, 6y minus 3y is 3y. So 1 by 210 into y equal to 0 to 5, 27 plus 3y by dy. So 1 by 70 into integration y equal to 0 to 5, 9 plus y dy. So 1 by 70 into 9y plus y square by 2, which is 23 by 28 is the probability of this one, p greater than 3. Now, the last one, probability of x plus y less than 4. So integration 0 to 2 and y equals to 2 to 4 minus y. So 1 by 210 into 2x plus y into dx dy, and 1 by 210 into y equal to 0 to 2 x square plus xy limits from 2 to 4 minus 5. Then I'll get 1 by 210 into y equal to integration y equal to 0 to 2 12 minus 6y dy. So 6 by 210 into 2y minus y square by 2 from 0 to 2. So 6 by 210 into 4 minus 2, so 2 by 35. Therefore, the random variable uh, x and y are mutually independent if f of x comma xy of x comma y equal to fx of x into fy of y, then x comma y are said to be mutually independent units. Now we'll check this with problem. Show that the joint probability function fxy of x comma y equal to 9 into e power minus 3x into e power minus 3y, where x comma y greater than or equal to 0 and 0 otherwise. Is it a valid density function? Also check whether the random variables are mutually independent or not. So first of all, I'll check whether this function is a valued function or not. That means it is a probability density function or not. So it is the function is said to be probability density function if integration minus infinity to plus infinity, integration minus infinity to plus infinity, f of x comma y dx dy equals to 1. So double integration x equal to 0 to infinity, y equal to 0 to infinity, 9 into e power minus 3x into e power minus 3y dy dx. So 9 times of integration 0 to infinity e power minus 3x into e power minus 3y by minus 3 from 0 to infinity dx. So 9 times of integration 0 to infinity e power minus 3x into 1 by 3 px, which is nothing but 3 times of e power minus 3x by minus 3 from 0 to infinity by 1. So therefore, double integration of f of x comma y dx dy equals to 1. So the given function is a probability density function. Now I'll find what is the marginal function of x. So minus infinity to infinity f of x comma y dy equals to integration 0 to infinity 9 e power minus 3x into e power minus 3y dy. So answer is 3 into e power minus 3x. Similarly, marginal function of y, integration minus infinity to plus infinity f of x comma y dx. So integration 0 to infinity 9 e power minus 3x into e power minus 3y dx. So 9 e power minus 3y constant, e power minus 3x by minus 3 from 0 to infinity. So 3 into e power minus 3y. Now fx of x, that means marginal function of x into marginal function of y. So 3 into 3 9 into e power minus 3x into e power minus 3y, which is equals to probability density function of x comma y. Therefore, the random variables x comma y are mutually independent events. So this is about the continuous random variable and its properties. Thank you.